So we're starting the disk method, or volumes of revolution, okay? So here's just a basic example of kind of what we're going to be doing. So we have this volume that we need to find. The solid is created by an area bounded by these three equations. So y equals negative x plus 1, y equals 0, and x equals 0. And we're revolving it about the x-axis. So that's what this arrow is showing us. It's showing us that we're revolving the x-axis. So it'd be like if we grabbed the x-axis with our fingers and started twirling it around. Okay? So basically what will happen is that this point right here, as it rotates, is going to go around like this. It's going to keep going around. Okay? Same thing, you pick any point on here, and it's going to keep going around like this. Okay, so the easiest way of doing this, and what I tell my students is, wherever your region is, and this blue area is my region, the first thing I tell them to do is reflect it over whatever is being rotated, your axis of rotation. So basically, this right here, reflected over, looks something like this. And then when you start adding in those circles, it'll start to look like a three-dimensional figure. Okay? So for instance, I'll do it a little bit better. Basically, this is what we're looking at. Now, if I looked at this yellow piece right here, if we looked at this, same thing, if I rotate it down here like so, and then we watch this piece, it rotates around like this, and this one rotates around like this, it's going to create this, you can't see it very well, but it's going to create basically a cylinder, and I'll draw it right over here. So it's going to have top like that, it's going to be down like that, and then it's going to create this little cylinder where here's the rectangle starting right here like this, and as it goes around, it's going to create this cylinder. Okay, so as soon as we see that we're rotating it around or revolving it around the x-axis, we know that this is the equation we're going to use. Pi from a to b, and the radius in terms of x squared dx. So just like we were doing with cross-sectional volume, we need to come up with r of x. Okay, which is basically saying the radius of this disk, this radius in terms of x. So again, we look at this from here to here, this is my radius. And again, we're talking about this vertical strip here. And we know that the radius, that length, is the function on top minus the function on bottom. We've been doing this for a while now. Okay? So this length of this piece is top minus bottom. So we're talking about the top function, which is negative x plus 1, minus the bottom function, which is 0, which gives us negative x plus 1. So that's what my radius is, negative x plus 1. Now, my volume starts, we need our upper and lower limits. Well, my volume starts here at 0 and ends here at 1. So my function here, my integral, is going to be pi from 0 to 1. My radius is negative x plus 1 squared dx. Now, that's it. That's my setup. So now I'm just evaluating this integral. So now that I've got my equation set up, all I have to do is evaluate it, and we're back to a definite integral. Okay? So there are two ways of doing this. You can either do it with U substitution, as we have a function inside of a function, or you could FOIL it all out and do it that way. Either way. Okay? So I'm going to do U substitution. So in this case, I'm going to say U is negative x plus 1, which means du is equal to negative dx, which means negative du equals dx. Now, the other thing I'm going to do is I'm going to change my upper and lower limits. So if u at 0, I plug in 0, I get 1, and u, when I plug in 1, I get 0. Okay, so here we go. I'll rewrite my integral, so I get pi, the integral. It's now from 1, since I'm changing my limits in terms of u, I get from 1 to 0 of u squared times negative du. Okay? Now, first thing you notice, this negative, I'm going to move it out there, okay, to make that positive. But notice I'm from 1 to 0, which means my limits are backwards, so I reverse my limits and I change my sign. So when I reverse the limits from 0 to 1, this negative will become positive pi, and this ends up being u squared du. Now add 1 to the power, divide by the new power, so I get pi times u cubed over 3 from 0 to 1, which means I end up with pi times 1/3 minus 0, which ends up being equal to pi over 3. And that is my volume. Now, super simple, right? Just definite integrals. Which makes sense, because, okay, let's look at it this way. This, if you look at the shape, ends up being a cone. What's the equation for the volume of a cone? It's 1/3 area of the base times the height. And in this case, we're talking about a cone, so it's 1/3 pi r squared times the height. Well, the radius is from here to here, which is 1. The height is from here to here, which is 1. So we get 1/3 pi times 1 squared times 1, which equals pi over 3, which gives us the same thing that our integral does. Okay? So again, be careful. Sometimes when you do these, you don't even have to do the integration. It's kind of like when we did area under the curve. If I'm doing area under the curve and I have a function, just a linear function, and I ask you to find just the area of this triangle, would you sit there and do an integral and do the integral from 0 to 1 under that equation? No. You just use the equation 1/2 base times the height. Okay? So when you get situations like this where you have just a cone or something, make sure you at least check yourself if you can to make sure that this and that answer ends up matching. But that's solids of revolution.